This presentation will primarily deal with batteries and fuel cells. There will be a couple others to cover topics about other practical electrochemistry matters. We will describe the electrochemistry of common batteries and will distinguish operation of fuel cells from batteries. The first battery was called the Daniell cell. It was not very efficient. It contained highly corrosive acid, and the salt bridge was porous clay. As a result, it was not very portable, very breakable, very dangerous, but it was a major technological advance. So this galvanic cell was composed of zinc and copper. We have come a long way since this was made. Modern batteries are manufactured to specific standard forms, so they fit in our electronic devices. We've all used them. We have all replaced them at some point. Now, batteries may be rechargeable, in which case they're called secondary cells, or they may be disposable, in which case they're called primary cells. Either way, their efficiency and safety is much greater than it was. Even with batteries causing laptops to catch fire sometimes, safety is still better than with easily broken materials containing concentrated acids. What follows is an overview of batteries that you are most familiar with. You do not need to know the information about these batteries. It will not be on the test, so skip it if you want. I just think it's cool, so I decided to cover it. So we usually call batteries nowadays dry cell batteries. We no longer have pools of liquid. Instead, we used paste. So let's start with the one that you're probably most familiar with, the zinc graphite battery that your single-use batteries are. So there's a paste of manganese oxide, zinc chloride, and ammonium chloride with a little bit of water. I stress a little bit because it's paste. And we're looking at a zinc magnesium oxide reaction. These are your A, AA, AAA, C, D, etc. Their potential is always 1.5 volts because that's what you get from zinc and manganese oxide. But larger batteries, because they have more reactants in them, can transform more coulombs. So they have a higher number of amp hours. In other words, your D battery will transfer more power than your AA. So my fundamental question for you is, why do these batteries have expiration dates? And I want you to remember that galvanic cells, the process is spontaneous. So if you think about it, you are continually doing the reaction here, even if the cell is not set up to extract those electrons. So that battery is going to go dead no matter what you do with it, and you have to keep replacing it if you want to keep using it, even if you don't actually use it for power. All right, so let's talk about rechargeable batteries. And these are nice and nasty toxic because they have cadmium. They're often called NiCad or nickel-cadmium batteries. So they are in a sandwich design, so it alternates back and forth between cathode and anode, which increases their efficiency, sometimes called the jelly roll. But the basic idea is that you have a nickel-plated cathode and a cadmium-plated anode with a potassium hydroxide electrode, and then you have a separator in between each of these layers. But because cadmium is toxic, you cannot throw them in the normal waste stream. Or you can, but you would then be risking the health and safety of everyone around you. We know that they can be in the same size and shape as AA's, AAA's, etc. So you could use them in all the same places you can our normal batteries. But in addition, they also get used in very large size for things like uninterruptible power supplies. When a hospital needs backup power or that kind of thing. This is a possibility because it's less expensive than, say, lithium-ion. And speaking of lithium-ion batteries, they are also rechargeable, so they are secondary cell batteries. And we know that they're in computers, phones, and electric vehicles. The reason that we like them is because they're pretty light. They provide a large current, a near constant voltage, and they slowly lose charge when stored, unlike our dry cell batteries at the very beginning. The zinc graphite loses charge pretty fast, but the lithium ion does not. Again, it's spontaneous, it'll happen. The actual voltage will vary because it depends on the amount of stuff that they put in, so the X in the formula above, but it's usually around 3.7 volts. You can take a look at whatever battery you're currently using for your computer, and it will say right on the battery exactly what kind of voltage it's putting out. You need a fairly stable voltage in order to run something like a computer accurately or a phone accurately. And they, unlike the NiCad, can take up to like 3,000 cycles before they die. Kaputskis. So how does this work? You have a bunch of solid things, and you are transferring electrons between them. So you can see in that picture, we're getting discharge from the graphite layers, which is being taken in by the lithium oxygen layers. Okay. Brings us to good old lead acid batteries. You probably have one in your car. They are ubiquitous as car starters. There are not a lot of other uses because they're actually really damn heavy. And although they give you a nice high voltage and high current density, you don't actually need that most of the time. So we're matching lead with lead oxide, and we do that in the presence of sulfuric acid. And I looked it up. The molarity of that sulfuric acid is somewhere between 3 and 5 molar. It's a strong acid, and it's diprotic. You can see how this would give you a very, very low pH, which is why if you ever see a lead acid battery leaking, you should probably go get some sodium bicarbonate and neutralize that shit, assuming you don't want to burn yourself. Okay, which brings us to the topic of fuel cells. So fuel cells are still galvanic cells. They use, instead of metals, they use combustive fuels continuously supplied. So this is sometimes called a flow battery. So what do we mean by combustive fuels? I mean literally stuff that we would burn. The most popular one that gets talked about all the time is the hydrogen fuel cell. You may or may not be familiar with it, but the idea is you have no toxic waste products because it makes water. Yay! Which is nice. And it's high efficiency, 50 to 75% versus 20 to 25% for an internal combustion engine. But in order to use a hydrogen fuel cell, we know that we have to have a continuous supply. And where are you going to store that continuous supply of hydrogen? And also, where is it going to come from? Because it turns out hydrogen likes to escape into space. Both of those problems are things that have not really been solved. It's hard to store at a small space, and it's hard to get enough to run the vehicle, because these were proposed for cars. And as a result, we do not have hydrogen fuel cell cars yet. It is a technology that people are still working on because having that little waste is actually really, really nice. You know, we have all sorts of nasty and toxic stuff that we get from our internal combustion engines, but this would not be that, and that would be nice. Okay, so this is the stuff you do actually need to know. Battery efficiency versus functionality determines the size and shape of your electronics. Primary cells are single-use batteries, secondary cells are rechargeable batteries, and finally, fuel cells or flow batteries pollute much less but are less efficient and take up a lot of space. So the hydrogen fuel cell of the future that we keep dreaming about still is not here because we can't come up with a good way to store it so that you can take it with you.